Anchorage, Alaska, March the 27th, 1964. In the port of Valdez, a Russian freighter has docked. A sailor takes out his camera and records these scenes. It's 5:36 p.m. and the light is fading fast. Suddenly, 100 kilometers away, the ocean floor rises by 10 meters along an 800-kilometer rupture. The sea drains away from the coastline. Ships keel over as the harbor empties. Somehow, the sailor keeps on filming. In front of him, a deep fissure opens up, and the sea pours back. A huge tsunami will lift the ship and move it inland, right out of the dock. In the city, the ground liquefies. The land tilts and slides, taking buildings with it. Afterwards, they take stock of a demolished city. 200,000 square kilometers has moved, the largest continuous landslip in earthquake history. The shock waves from that massive earthquake were recorded all around the world, and 10 minutes later this record was received in England. It continued for several hours. And it's signals like this that have passed right through the Earth that seismologists use to study its internal structure. Now, in this program, we're going to find out about the way that the energy of earthquake waves passes through the Earth, at the way earthquakes are detected, and at the way seismologists use them to find out about the Earth's internal structure. But what does it feel like to be in an earthquake? Well, there seems to be an earthquake going on here. Just look at the flowers and at some of the other objects in the room. They're vibrating because the whole room is shaking. It's a little bit like what happens when a heavy lorry goes past your front door and energy is transmitted through the ground. Now, this kind of vibration represents 0.3 on the scale of earthquake intensity devised by the Italian seismologist Mercalli in 1902. Well, I'm not in a normal office. We've built this one on a special earthquake simulation shaking table at the University of Bristol. And we can reproduce any intensity we like. The computer control system generates different kinds of movements on the table through 8 hydraulic rams that are connected to its base. So let's see what happens if we increase the intensity to Mercalli 5. Well, things are moving around a bit more. You see the cup shaking on the wall, the lampshade, and the flowers vibrating around. And watch the candle. So let's increase the intensity a bit more and see what happens. It's actually getting a bit dangerous in here, so I think I'll beat a retreat. Well, the walls finally fell down, and that's equivalent to 0.8 on the Mercalli scale. We're now close to the level of total chaos that's so distressing for people who are caught in Mercalli 9 and more intense earthquakes, where the ground motion's so uncontrollable and unpredictable. And that's why we need to study earthquakes and understand how seismic energy is propagated through the ground. But what's the nature of the vibrations that causes all this damage? Well, if a column of rock is suddenly compressed, a pressure pulse moves rapidly through the block. The squares remain rectangular, but change in size. Successive compressions and dilatations pass along the column, forming a train of compressional waves. But if the column of elastic rock is jerked sideways, a shake or shear wave moves along the column. Now the individual squares do change shape, but these S waves travel only at about half the speed of P waves. So how are earthquake vibrations detected? Well, this ancient Chinese instrument illustrates the principle. It was devised by the philosopher Cheng Heng in AD 132. When there's a sufficiently large ground vibration, the body of the instrument moves, but this heavy mass inside tends to stay where it is. Now, by a system of levers, this causes the mouth of a dragon to open so that a ball falls down into the mouth of a frog beneath. Now, in Cheng Heng's original instrument, there were 8 dragons and frogs, and that meant that not only could he detect when there had been an earthquake, but also the direction from which it had come. For example, if it came in a different direction, a different mouth would open. Now, modern instruments, like this one, use much the same principle. Inside here, we have a heavy mass mounted on springs. The mass itself is magnetic, and inside there's a coil, so that when there is a disturbance, one can see a signal generated, an electrical signal, due to relative movement between the magnet and the coil. The advantage of instruments like this, of course, is that you can get a continuous record of a seismic event. Well, instruments such as these are used in most observatories around the world today. Peter Marshall's interested in detecting and identifying nuclear explosions as part of a global seismic detection monitoring network for the British government.
Inside this seismological vault, we operate several types of electromagnetic seismographs. They sit on this concrete pier, which is in intimate contact with the bedrock, so that the seismic signals are transmitted very efficiently through the earth to the seismometers. This is a vertical seismometer. In the vertical seismometer, the case moves up and down relative to the mass. In the horizontal seismometer, where the ground is moving backwards and forwards, the case moves in a horizontal direction relative to the mass. The electrical signals which are generated, we can see the coil here, are taken away by leads and amplified. We can then transmit them to any recording station within a few meters, yards, or even many, many miles away. And this is what we do. When we're recording in anger, we wouldn't leave the seismometer in this way. We would need to protect it from the environment. The effect of the atmospheric pressure variations can be quite severe on seismometers, as indeed can temperature changes. And so what we want to do is to really put a case over these to isolate them completely from these extraneous effects. That's a source of really unwanted noise for us, and we want to minimize these noise effects. Now, this is quite a large instrument. There's been a great deal of progress recently, not only in electronics, but in seismometer mass instrumental development as well. And to take advantage of that, we can make much smaller and much more sensitive instruments. Now, as an example of this, 2 very modern instruments are shown here. They look just like tins of beans. In fact, they're really very, very sensitive instruments. These, in fact, are so sensitive that if you wanted to, you could pick up a chicken pecking corn from about 10 meters away. However, the ambient background noise is too large to enable us to do that. What we can do is demonstrate how sensitive these instruments really are. So let's see. I'll tap the side. Now, how can we take advantage of this massive improvement in sensitivity and micro-miniaturization of the electronics and the components? One way we can take advantage of these developments is to actually operate the seismometer, now that it's nice and small, down the bottom of the borehole. This has the added advantage that we can actually take advantage too of this increased sensitivity. Now, why operate down a borehole? Well, by going something like 40 meters down into that bedrock, we're getting away from all the surface effects, which generate background noise, which is unwanted, thus enabling us to see the seismic signals more clearly. Now, in this borehole package, we have 3 seismometers. 2 are recording the horizontal ground motion, and one of them is recording the vertical ground motion. The very weak signals that are coming out of the seismometers are passed by cables up into the electronic package. From there, the amplified signals are taken away by the cable to the recording stations. Incidentally, as I leave, see if you can see my footsteps on the recorder. The output from the seismometers which are located in such vaults as we've just seen can be recorded in many ways. One way of recording them, of course, is onto paper. And this gives us a visual recording of the previous 24 hours recording. A much better way of recording is to record on magnetic tapes, because in this way, the analyst can do many more things using computer techniques. Now, in this room, we have a whole batch of tape recorders, and we need a large number of tape recorders because we're going to record the data continuously, and we're also going to record from a whole number of stations. What we're actually doing in this room is recording the output of 9 seismic stations from what is called the United Kingdom network of stations. They stretch from as far north as Eskdalemuir in Scotland to Cornwall in the south of England. This network of stations, in fact, forms really just part of a global network of seismic stations, the outputs of which are all being recorded on magnetic tape. We've been recording earthquakes for over 25 years now, and in that 25 years we've acquired an enormous amount of data, much of it still available to us on magnetic tape. This enables us, in fact, to relive any of the seismic disturbances that we choose that have occurred in the last 25 years. To do this, we will simply take the tape, put it onto the computer, and we have the choice of either replaying onto a pen recorder, or we can display it on a computer VDU, or process it directly via computer. Let's have a look at an example of an output of an array located in India. We can call up all the individual channels and examine the output. We can remove the obviously noisy channels and ask the computer to search for the remaining signal. You can see the noisy channels that we've removed by the black portions. Now we've got a much cleaner trace, giving an improved signal-to-noise ratio, which is much easier for analysis. We can then manipulate the signal to produce any desired output that we require. Here, for example, we're displaying the Mexican earthquake from the computer onto a pen recorder. It builds up to large amplitudes and then slowly decays away. But in fact, the ground vibrations from this earthquake could still be felt for many, many minutes afterwards by our seismometers. How do we know this was the Mexican earthquake? Well, enough people felt it and were able to tell us exactly the location of this. Now, that's not true for many of the earthquakes which occur in the world. Most earthquakes occur on clearly defined zones around the world. Many of these zones are remote from population and in fact do occur undersea. Now, how in fact are we able to locate these seismic disturbances? To do this requires a really clear understanding of how seismic waves propagate through the earth.
When a stone is dropped into a pool of water, circular ripples spread away from the focus, just like body waves inside the earth. Imagine P waves from an earthquake spreading down into the mantle. The wave front reaches the core mantle boundary 2,900 kilometers down in just 4 minutes. The speed drops dramatically at the boundary, but soon increases again. The central wave front penetrates the inner core at 8 minutes. It's now moving at over 10 kilometers per second and passes the center of the Earth in just under 10 minutes. The waves which just grazed the outer core reach the surface in 13 minutes at an epicentral angle of 103 degrees. At greater angles, there's a shadow zone where no direct waves are detected until at 142 degrees. Here, waves which have come through the core begin to arrive at 19 minutes. And seconds later, the wavefront which has passed right through the centre of the Earth emerges, having travelled nearly 13,000 kilometres in less than 20 minutes, an average speed of 39,000 kilometres per hour, 20 times faster than Concorde.
We've seen how P waves travel through the Earth. They're very, very fast. S waves, however, travel through the Earth much more slowly. It is this sort of information, gleaned from many, many earthquakes over many, many years, that has enabled seismologists to construct travel time curves. That is, the time taken for a wave to propagate against distance. Now, if you were at an angular distance of about 50 degrees, then you would expect a P wave to take some 9 minutes to arrive. The S wave will take somewhat longer, 16 minutes. And another type of wave which travels around the surface of the Earth, called a surface wave, takes even longer. But we'll just concern ourselves with the P and S waves. You can see that as you go further away, the time difference between the P and the S wave gets greater. And it's this information that we use to estimate the distance of an earthquake from a recording station. Now let me illustrate this with an example of an earthquake. I'm going to take this earthquake here. It's a fairly small earthquake, and I want you to ignore all these other traces. And let's start at the beginning here, where we just see the background noise. Then we see an emergence of a P wave, followed somewhat later by an S wave, and even later still by the surface waves. Now, if I note the arrival time of the P wave and of the S wave, I can estimate the distance. Now, I've drawn this travel time curve on exactly the same time scale as the seismogram. And so, by moving this piece of paper backwards and forwards between the P and the S waves until I get a fit, it will enable me to estimate the epicentral distance in degrees. Now, I can see there that I have quite a good fit between P and between S. And that gives me a distance of 22 degrees. Now, if I measure 22 degrees on the globe, and then put the compass on the epicenter, the station, and then draw a circle around that station, by drawing the circle, you can see that it intersects with two other circles which I've already drawn on the globe. This is station data from Moscow and from Jerusalem. The intersection of these three circles indicates that the origin of this earthquake was in fact in Romania. If I'd only had data from two stations, I would not have known whether it was there or there. The contribution the third station makes is to positively locate that earthquake in Romania. Now, once we know the epicenter of a seismic disturbance, we can use this to probe the Earth. In fact, earthquakes occur where they have to occur, and so we can find a lot of information about the Earth structure close to earthquake zones. However, to determine structure away from seismic zones, we need to use artificial sources. We can use a hammer for shallow investigations. The seismic P waves penetrate only a few meters deep and travel in the rock layers and subsoil at over 2,000 meters per second. The seismometer by the hammer is activated by the hammer blow and sends a signal along a cable at the speed of light to start the electronic trace. A fraction of a second later, the vibrations arrive at the second seismometer. Analysis of the first arrival times from progressively greater distances can be used to identify distinct boundary layers in the top 10 meters or so. To penetrate deeper than 10 meters just needs a bigger hammer. Surveys can even be done along the roadside. The principle is a bit different. Here we bang the surface and record the arrival of the wave reflected from layer boundaries a few kilometers deeper into the ground. At sea, you can trail detectors like a fishing line and use an underwater air gun to stimulate vibrations which couple through the water. The waves reflect off layers of sedimentary rocks tens of kilometers deep beneath the ocean floor. Even deeper probing is possible by setting off explosive charges within the ocean. But the biggest artificial hammers of all are underground nuclear explosions. Now the waves travel down through the crust and are refracted by the mantle before emerging at the surface, a journey of some hundreds or even thousands of kilometers. A really good example of how nuclear explosions have been used to probe the Earth occurred in the Soviet Union. This is a map which indicates the location of a large number of explosions, many of them which no doubt are nuclear. What is of particular interest to us with regards to deep seismic sounding is the line illustrated here, which is some 3,000 kilometers in length. Along this line, the Soviets fired a number of explosions. They were fairly small at this end, but increased in size as we went north. Now, what did the Russians find out from this particular line, this experiment? Well, at this end, close to the Black Sea, where the explosions were quite small, they were only able to probe down to the Moho, a depth of about 30 kilometers. And we can see that here, although they were able to resolve some of the structure within the crust. But as we go further north, and these explosions at these epicenters are somewhat larger, they were able to probe to a much greater depth within the Earth. And we can see here, for example, that not only were they able to define some crustal structure, the Moho, but they were able to define structure at a much greater depth. in fact, almost to 200 kilometres depth within the Earth. But of course, our job isn't to probe the Earth with nuclear explosions. What we're interested in is being able to detect and identify underground nuclear explosions. How do we do that? Well, let's take a look at some of the seismic signals that we've recorded from the Soviet Union. This map is, in fact, a Landsat image of the area of the Soviet test site. On one occasion, we did record this particular seismic trace here. And when we located the precise location of this, we found it occurred somewhere just here, which is very, very close indeed to this fault. You can see the fault very, very clearly. Now, the complexity that we observe in that record comes about because what an earthquake actually is the massive movement of one slab of rock relative to another. It's a very complex source. And all the waves that emerge get scattered, and we can see a very complex record. Let us compare, for example, now, the very simple source that we see from the explosion test site. And this is the location of the underground explosion, and this is the signal that was generated. Note how simple it is. Now, this is not surprising, because what is an underground explosion? It's just a sudden release of energy, and it radiates outwards as a very simple pulse. Now, to differentiate between these two signals really wasn't very difficult. They were both large signals. The problem of discriminating between earthquakes and underground nuclear explosions comes from the very small events, where the source dimensions of both the underground explosion and the earthquake are very, very similar. And it's our role to pursue the research and development into techniques to really identify the very small nuclear explosions which occur amongst the many, many thousands of naturally occurring earthquakes.
Well, so much for seismic signals, but what can we do to mitigate the damage that they cause? Well, this is where engineering shaker tables come in useful. And here at Bristol, they're investigating the structural stiffness of building frameworks and are deliberately developing structures that absorb earthquake energy by flexing laterally rather than by collapsing vertically. Another approach is being investigated here, on one of the world's largest simulators next to the San Andreas Fault at Berkeley, University of California. Here they're trying to isolate the ground vibrations from the building. A 50-ton steel frame is mounted on long-lasting stiff rubber blocks, which are particularly effective at isolating high-frequency components. Already, these base isolators are being incorporated into some Californian buildings. But no matter how successful are our attempts to mitigate the effects of earthquakes by designing earthquake-resistant buildings, nevertheless, earthquakes still cause damage to essential services and loss of life. So the challenge to the scientist is to predict when and where an earthquake will occur. Unfortunately, earthquake predictions are very inexact science. Some of the methods that have been used with limited success involve monitoring well water levels of radon gas emissions and of general inflation, ground inflation in earthquake-prone areas. Changes in seismic wave propagation velocities have been used with some success, and perhaps one of the least understood but most successful methods has been observations of changes of animal behavior, which have been used by the Chinese. Now, to the geophysicist, earthquakes provide one of the most powerful methods for studying the Earth's interior. But earthquakes are also a spectacular demonstration of the dynamic forces that operate and generate movements in the Earth's outer shell. But to the engineer, the problem is to design a safe environment in which to live.